Hey guys, so today we're going to be talking about some basic probability, doing some questions, as well as talking about independent and mutually exclusive events. So, this is what we do. If each outcome is equally likely for a scenario, so this could be let's say a dice roll, such as the chance of each of the sides equal, or a coin toss. So all these things, each outcome is equally likely. So to work these out, you go the number of outcomes that satisfy whatever you're talking about. So if it's saying, let's say, the probability of an even number, you would have the 2, 4, and 6 for a dice roll. So it would be 3. So there are 3 outcomes over the total number of outcomes. So it would be 6. So therefore you get 50%. So this is pretty important. But note, it's only when each outcome is equally likely. So, we'll start off with a question. So an example. You have a bag. And inside this bag, you have 6 white marbles, 8 blue marbles, and 4 red marbles. So these are all in the bag. So there's nothing else in the bag. So you randomly select one. And you can just assume that they're all mixed up. So yeah, it's like before. There's for you to get one marble, there's the same likelihood of picking another one. So what's the probability that you pick a red one? Well, there are 4 red marbles. So 4 divided by the total. So to work out the total, you find out, well, there's 6 white, there's 8 blue, and there's 4 red. So it's going to be 6 plus 8 plus 4, which gives you 18. 6 plus 4 is 10, plus 8, 18. So therefore it's 4 on 18. So the probability of getting a red equals 2 on 9. And as I said before, typically in these questions you either give them as a fraction or a decimal, and 2 over 9, if you want to use a scale, you have 0, which is never going to happen, 1, which is certainty. Yeah, it's about there. But you don't need to think about that. It's just trying to graphically represent the probability and working out how likely 2 over 9 actually is. So what about if you want to know the probability that you pick a random marble and it's either white or it's blue? So there are 6 white ones, so they contain in there, but there's also 8 blue ones. So whether you pick a white one or a blue one, they both satisfy. So we need to include them both, and then divide it by the total. And that gives us 7 over 9. Gives us 14 over 18, simplifies to 7 over 9. So you can work out any other question in which there's equally likely by doing this, and we'll do some later techniques to graph it and to do some more complicated questions. But just looking at those results, we had the probability of red was 2 over 9. Then we had the probability of white or blue as 7 over 9. Now if you add those together you get 1. Now this isn't a coincidence, because with the probability of white or blue, you could sort of think about this as the probability of not red. Not red. Because there's only 3 outcomes, white, blue, or red. So the probability of not getting a red one is 7 over 9, as we previously calculated. And then the probability of red equals 2 over 9. And so that gives us the important relationship that the probability of, I'm going to call A red or white A, as I've done before, just A represents any event, subset, A dash equals 1 minus probability of A. Now, this A dash means not A. So it encompasses everything in the set that isn't A. And that's encompassed by that A dash. So this is an important formula. And then you could do it the other way around. If you plus probability of A minus that one around, you'd also get the probability of A equals 1 minus probability of A dash. But typically you already know the probability of A and you want to know the probability of A dash. So you can use this formula to calculate it. So, where does this formula come from? Well, think about it. Here, 1. We talked about it before. That's certainty. And then you're minusing the probability of A. So, if you're thinking about any outcome, if you say the probability of something happening is 20%, the probability of it not happening is 80%. And that logically makes sense because it is the certainty of, we're assuming for these outcomes that the event is going to occur. For example, the marble, there's not the option that you don't pick one. You have to pick one. So there is certainty, that's where the 1 comes from, minusing the probability. So memorize the formula, but also you can think about it. An easy example is 20% of something happening. What's the chance of it not happening? Well, logically, it would be 80%. Just quickly, I didn't mention it in the previous video, introduction to probability, but I probably should have. That the sum of all the probabilities of the set has to equal 1. And so this sort of makes sense with that. What this is, if you remember, this is a set. So it encompasses all the outcomes. So what this means is that you can't, it has to equal 1. There has to be certainty. If you add the probability of every single outcome, all the outcomes that could occur, then it should be 1. Now, this makes sense, but you have to be able to apply it to different scenarios. So, we'll use an example. You have a running race. And there are 3 people in this race. John, Sam, and Hugo. And so you have the probability down here that they're going to win. So let's say there's 50% chance John is going to win, 20% Sam's going to win, but we have no idea what the chance of Hugo. So I'm just going to represent it by X. But we can actually know what this is. If we know that somebody does have to win, and these are the only 3 people, then we can use this. The sum of all the probabilities has to equal 1. Because, yeah, as I just explained. But, if you apply it, you can go 0.2 plus 0.5, sorry, plus 0.2 plus X equals 1. That gives us 0.7 plus X equals 1. So X equals 0.3. So Hugo has a 30% chance of winning. So once again, when you put in this scenario, you might not initially pick up at 0.3. But if you word it differently and say, there's a running race, John has a 50% chance of winning, Sam has 20%. If Hugo's the only other competitor, what's his chance of winning? You'd probably say, 30%. But this is putting into a mathematical formula and a mathematical notation. And that's also important for later mathematics, if you haven't already done it already, that this symbol here means the sum of. Yeah. Now, 2 other really important terms are independent events and mutually exclusive events. So these 2 terms are to describe the relationship between 2 events. So as I said, events are sort of subsets of what's occurring. So an example of independent events, before I give any mathematical, are dice rolls and coin tosses. So independent events are when the outcome of one of the trials, one of the dice rolls, one of the coin tosses does not affect. Yeah? So it does not affect the outcome of another one. So if you put into practice, if you roll a dice and you get a 2, what is the probability that you'll get a 2 the next time? Well, it's still 1 on 6. It's always 1 on 6. With a coin toss, it's 1 on 2. It's always 1 on 2. So another way of thinking about it is it has a constant probability that no matter what happens, no matter what outcome, the probability remains the same. So you think, oh, maybe that's most cases. But there are lots of cases where the outcome of one therefore changes the chance. And the most common one is the weather. If it rains one day, the chance that it rains the next day has definitely increased. So let's say this is Monday. The chance of it raining is 20%. And then what's the chance of it raining Tuesday? Well, it could be 20% if it doesn't rain on Monday. But if it does rain, Tuesday could go up all the way to 50%, for example. And so there are later questions in which you have these different changing events that are not independent, and we work out the probability. But for independent, think about it like dice rolls and coin tosses. So the mathematical definition for independent is that the probability of the A intersection B, so these are the events we're talking about, A and B, equals the probability of A times the probability of B. Now remember what I said about intersection. You can sort of think about this as both. So the probability of A occurring and B occurring equals the probability of A times the probability of B. Now normally I like thinking logically about these questions. However, for this formula it's better to just accept it, as it is a little bit counterintuitive. But yeah, just remember this and we will later use it. So the probability of A times the probability of B equals the probability of A intersection B. But remember, what does intersection mean? It literally means A and B both occurring. Now, mutually exclusive events. This means, as I say, they're exclusive, and if one event occurs, the other can't. So, if you, let's say it's a race, if you get gold, you can't get silver. So these are mutually exclusive events. So the probability of getting silver if you've already got gold is 0, because that means you've already placed first, so you're not going to get second. And the other way around, if you get a silver, you're not going to get gold. But there are lots of different other scenarios. So mathematically again, this is a probability of A intersection B equals 0. So the probability, putting into actual words, the probability of A and B both occurring equals 0. And so these are two really important definitions. And these will make a bit more sense when I go over Venn diagrams, as graphically it makes, especially mutually exclusive, you can see how when two events are not the same, they have no intersection. Alright, thanks for watching guys, and I'll see you next time.